All right, friends, we are waiting for others to join in. Okay, so we'll wait 1 minute at least and see if others are joining. Okay, I'm audible clearly, right? Okay, good evening, everyone, though. Okay, how did you find the previous assignment, physics assignment or homework? Have you guys all tried? How did you find it? It was all easy. Which ones are confusing? Okay, some are confusing. Yeah. Some there has to be struggle, right? If you don't struggle, that means you already know everything. So why you're solving it, right? So while you solve problem, remember in class 11th, when you solve problem, 60 to 70% of learning will be happening when you solve problems. So many times you may feel as if you don't know, or this particular thing was not taught also. That kind of feeling will also come in your mind. Okay, but the thing is that it is all you have to apply the concept in a different manner, right? And there are million ways in which you can apply the same concept. So we cannot cover each and every way the concept will be applied to solve millions of problems. Okay, so it will become a habit. Whenever you look at something new, how you approach it, that habit will only help you in exam like JEE or NEET. Because when you write these exams, you may feel that half the problems are completely new, you have never seen it. So there comes these kind of learnings handy if you know how to deal with something which is new. I cannot find the normal. Okay. Or which case you are not able to find the normal? Which one? Okay, fine. So, you, or you can just take one or two pics of the questions and send it across. So maybe when I explain that in the group, okay, when I solve it and send it across to you, then you will understand how other problems can also be solved. Okay, just take one or two such questions and send it across. Fine. Okay, Priyam, what exactly you found difficult? Gurman, have you tried? Okay, some problems are tough. Yes, they are. Questions with motors. Questions with motors. So Priyam, you take a pic of the questions with motor, right? And send it across in the group. That is what the group is for. The group is not for us to send you the class reminders only. That is the least thing that is expected in the group. The group is made so that you can put your doubts in the chat, and then we can discuss it, right? So when we discuss the problems in the group, the learning becomes better. And if we discuss these problems right now in the class timings, then half the class timing will just go in solving those doubts. Okay, but I'm not saying that we'll not take up the doubts. You put it on the group, okay, and then I will schedule a separate session, probably in the morning or sometime. If there are too many doubts, I'll separately schedule a session and we can discuss those doubts if there are many in numbers. Otherwise, most of the time, when you put a question in the group, we will just solve it and put it again, and then you will understand how it was solved. Changing acceleration. Okay, how to identify the side in terms of cos theta, sin theta. Okay, so you if you want to find out the sides using sin theta, cos theta, you need to first identify the right angle triangle. Okay, create a right angle triangle, then sin theta is perpendicular upon hypotenuse, cos theta is base upon hypotenuse. So again, Oro, the thing is that you need to show the problem. We cannot talk in air, right? So if you put a question, then we can discuss it, that this is how you have to find sin theta in this case. Then that case will help in other cases as well. Same with Oshik also. You can also do that. Fine. All right, guys. So let us start the today's session. And today is the last session on the bridge program. After today's session, probably we'll start the your class 11th curriculum. Fine. And yes, a lot of doubts are expected, and you guys are doing exceedingly well. Even if you're getting 60% of the questions in the homework, it is a very, very good percentage. Don't fool yourself believing that you need to get 100% questions right. Okay, this is not your school type of exam wherein everybody is scoring 100%, so you also have to score 100%. Fine, at this point in time, 50 to 60% is a decent performance. Fine, so don't be very hard on yourself as well. All right, guys, put your doubts on the group. We'll discuss it. If there are too many, we'll schedule a session which is exclusively for the doubts. So today, as you can see in front of you, the topic is free body diagram. Okay. Now, can you tell me, have you ever heard about this? Have you ever heard about free body diagram? All of you? Yes, Anushka is saying, Oro is saying. Okay. What have you heard about? No. Some of you haven't heard about free body diagram. That is absolutely fine. When I teach something, I will teach from the start. It will from the scratch. Whether you know or not, it doesn't matter. In fact, if you don't know, it will be better. Why it will be better? Because then you will not be relating what you already know, what someone has already told you, and then you'll get confused a little bit. So if you don't know anything, that is the best actually. But anyways, what do you know? Oro and Anushka, what do you know about free body diagram?
It represents the forces acting on a particular object.
Very good. So I think Oro also meant same thing. Same. Okay. All right. So write down free body diagram. Free body diagram. You might be knowing, and probably I might have already told you this thing, that your 80% of curriculum of class 11th is what? Mechanics. 80% is mechanics. Fine. And when you solve problems in mechanics, you'll be dealing with forces. Fine. And you'll be dealing with the motion. Forces and motion you'll be dealing with. That is the heart of mechanics problem. Any mechanics problem, forces and motion. Fine. We have already done one tricky part of the motion, which was constrained motion. Okay, so constrained motion is the trickiest part of the motion, and now we are doing the part which is trickiest with respect to forces. So we are trying to understand how you represent a force. All right, so in a way I am trying to enable you to solve problems, and these are the important steps of solving any problem in mechanics, constraint motion and free body diagram. We are not solving the complete problem, by the way. The problem will be, some situation will be given to you, and they might be asking you what is the force on this body or what is the acceleration on some other body. Okay, but when you try to find out the acceleration and try to find out the forces and all, you must have to deal with the constraint motion and the free body diagram. Okay, so that is what we are doing in the bridge program. So you'll see that when you will be doing chapters like rigid body motion, laws of motion, work energy chapter, you'll see that your understanding has gone up multifold and you're able to solve problems so easily, whereas the others will be struggling. Fine. So that's the reason why free body diagram has been picked up. All right, and as the name suggests, today we are going to draw a lot of diagrams. Okay, today's topic is all about diagrams. Sir, my internet got disconnected. Okay, now it is connected, or you can use a mobile phone in case of emergency. Feel free to use mobile phone, but I won't recommend that. If you have broadband connection, please use the desktop or laptop. Anyways, coming back, free body diagram, as someone has already said, is a representation. Please write down. It is a representation of forces. Representation of forces acting on a body on one body at a time. Okay, you should not draw multiple bodies because it is a free body diagram. It's not free bodies diagram. And what is force? Which type of quantity? Scalar or vector? It's a vector quantity, right? So how you represent a vector? How you represent a vector? Using arrows, right? So it is a representation of forces acting on a body by using arrows. Okay, see how simple the topic is. But what we have to do, you can see here, the first page was free body diagram only. So here multiple forces are shown. Fine, something like this only we have to show. But then here more than one bodies are together. All right, we'll be drawing one body at a time. But having said that, this is what we are trying to do in today's session. We are going to take the object and represent forces on it, period. Fine. Now when we'll be representing the forces on a body, we need to understand few things. What are those few things? Behavior of the object. You need to understand that, otherwise how will you know how it will behave when forces are acting? And you need to also understand the behavior of forces. When I say behavior of forces, there are multiple kinds of forces, right? There are forces like gravity, which will be something, and there will be forces like friction. So we need to understand all these forces one by one. And once we understand the behavior of objects, and once we understand the behavior of forces, then we can use these understanding to create a diagram or create a representation of all the forces. Fine. So this is what is the today's topic. Now, correct. So now when we are talking about behavior of objects, fine, what comes in your mind when we talk about behavior of objects? What is the first thing that come in your mind? Behavior of an object or behavior of a mass, or how something is moving. Nature comes in your mind. Okay, what else? What the object is doing. All right. Have you heard about the Newton laws of motion? Have you heard about Newton laws of motion? Right. So that should come in your mind. Newton laws of motion is what is the first thing that should come in our mind whenever we are trying to find out how an object will behave. Okay, now you will see that the laws of motion is a separate chapter in your class 11th curriculum. It is chapter number 3 or 4, and it is considered to be the most basic chapter of a class 11th. All right, so we are not going to study this chapter completely, but we are going to just learn few things from that chapter so that we are able to draw the free body diagram. Okay, so we learn only the basics of laws of motion. Okay, so of course when you hear word laws of motion, Newton's name will come in your mind. Laws of motion. You know how old the Newton was when he discovered everything, whatever he has to? At what age? Not 19. He was around 23 to 25. Okay, around I think 22 at 25, whatever the age was. He was pretty young. Okay, he has uh, discovered uh, many things. He has formulated entire mechanics, which you are studying. 80 to 90% of what you are studying is what Newton has done. In class 12th, you'll be studying optics. Newton has done that. Okay, Newton has contributed, and half of the mathematics, which is calculus, Newton has huge contribution in that. So towards the later part of year, Newton was struggling with the chemistry. He was trying to create he was trying to create a gold out of mercury or some other metal, but then he was not successful. But anyways, he has contributed a lot, and since he was the first person to list down the laws of motion in a very crisp and very systematic manner, the laws of motion are also called Newton laws of motion. Fine. So having said that, it is not that only Newton has understood these laws. Many people like Galileo before him has contributed many things about how objects are moving. But Galileo was more of experimental in nature. He used to do experiments, as in, he used to say that based on my experiments, feather and the stone will hit the ground at the same time if air is not there. So he used to give experimental results. He never used to give certain kind of laws or something which is always true. So Newton was the first person who started giving universal laws, which is always true. So that is why these laws are also called Newton laws of motion. Okay, so we'll discuss it one by one. I'm sure you have heard about Newton laws of motion several times, but you'll see many insights are there which we miss. Okay, so all of you write down first law of motion. First law of motion. If you just write first law, it doesn't mean first law of motion. If you just write first law, it means thermodynamics first law. Okay, so do not just write first law ever. So first law of motion. If suppose a child comes to you who is very young and he wanted to understand what this law is about, what this law is trying to say, how will you explain? What should be the heading of the first law of motion? What do you think? I'm sure the statement you might be knowing, but what is trying to tell? First law of motion is telling you what? Okay. All right. See, the word like inertia you should not use, because inertia is not a common word and the child may not know, right? So how will you explain it? What does first law tries to cover? Okay. More or less all of you are telling the same thing. Okay. All right. So first law of motion tells you about, it tells you about, I'll read message, what it takes to move an object. Okay. It tells you about how object, it tells you what, or it tells you what objects want to do, or it will tell about the natural behavior of an object. Behavior. The example of natural behavior is this. Suppose nobody is there to watch whether you're studying or not. Your natural behavior could be playing games on mobile phone. Okay, so that is what you want to do until an external force is being applied. That is your natural behavior. Nobody need to tell you to do that. This is something which come inherently. Fine. So this is what the first law of motion is, that the object, what object wants to do, it, first law of motion tells the natural behavior of an object. Okay, and what is that behavior? The object, the behavior is the object doesn't want to change its state, period. Whichever state the object is, object doesn't want to change its state. This is what the object natural behavior is. For example, if your natural behavior is playing games, okay, that is what you want. If I have to change that, if I have to make sure that you start studying, then I have to make effort. Okay, or your parents have to come and tell you that, listen, Oro, please study. Then you will listen. If then also if your inertia is very high, then also you don't listen. Probably both the parents have to come and tell you that, Oro, please study. Then only you will sit and study. Okay, so depending on how strong the behavior is, or depending on how much inertia you have, it will determine how strong this behavior is inside you. Okay, so first law of motion tells the natural behavior is the object doesn't want to change its state. And what is the state? State means what? There are two states in physics that are defined. Write down. Correct. There are two states: state of rest and state of uniform motion. Okay, state of, write down, uniform motion. Now tell me, is anything in this universe at rest? Is anything at rest? Nothing is at rest. You might be thinking that you are sitting in a chair and you are at rest, but do you know at what speed Earth is moving around the sun? Do you have an idea with what speed you are moving around the sun? You're moving around 12 kilometers every second, okay, around the sun. But even sun is not stationary. Sun is also moving. Even galaxy is not stationary. Galaxy is also moving. So there is no reference point which will tell you whether you are at rest or you are moving with uniform motion. Okay, there is no experiment in the universe which can tell you that you are at rest or moving with uniform velocity. That is why the theory of relativity has to come in. But then we are not getting into all that. When Newton was formulating these laws, okay, which we are assuming to be true, okay, he meant rest means relative to Earth, something is at rest. Suppose object is kept on a table, the object is at rest. You are sitting on a chair, you are also at rest. Okay, this is what it means when it say it is some object is at rest. What is uniform motion? Anyone? What is it? Uniform motion, what it is? Equal distance with respect to time, okay? Acha, tell me, is an object move with constant speed in a circle, is that uniform motion? Constant speed in a circle, is that a uniform motion? That's not a uniform motion. Okay, so uniform motion means constant velocity. Constant velocity. So it means no, not acceleration. Not acceleration. No acceleration should be there. So object moving in a straight line with constant speed. This is what the uniform motion is. Okay, so if object is at rest, object wants to continue to be at rest. If object is in uniform motion, object wants to be in uniform motion or continue to move in a straight line only. Okay, now this is what objects wants to do, and this behavior is universal. Everybody or every object on this universe wants to do that. So this behavior, we need to name it because very important behavior. So this behavior name is inertia. Okay, it is found out that more is the mass of an object, stronger the behavior it is. So inertia increases, or this want to do these two things, or want to maintain the state, that want, that willingness to do that is more when mass is more. Okay, now can you quickly tell me a few examples of these two, uh, inertia of rest and inertia of uniform motion? All of you, what do you want me to repeat? Behavior name is inertia, and inertia is proportional to mass. This is what I have said. Okay, now tell me the example. Inertia of rest. One example of inertia of rest, quickly. Okay, not able to? All right. Okay. When you're standing in a bus, suddenly bus starts moving. So your lower part of the body is moving with the bus, but the upper part of the body was at rest. So upper part of the body want to be at rest. So you'll be like that. You'll be as if you're falling backwards. Okay. One very common example is dusting a carpet. Very good example. So when you are dusting a carpet, what do you have to do? Suppose you have a cloth which has a lot of loose dust particle. What do you do with that cloth to remove the dust? You suddenly jerk it like this, right? You move it. When you move it suddenly, the cloth, or when you hit with a stick, what happens is that some portion of the cloth suddenly moves away. But the dust particle wants to be there only. So the cloth has gone away, but a dust particle which was loosely attached, since they wanted to be there only, the cloth went away and the dust particle will fell on the ground. Okay, this is what a dust particle wanted to do. Okay, and you might have played carom board, right, where you have stacked multiple coins like this. If you have stacked multiple coins like that, and suppose you hit with a striker the bottommost coin, what will happen to the above coins? Will they fall down or they just vertically come down like that? Have you played carom board? Okay, yeah, they will just vertically come down. If you strike fast enough, it has to be very fast, very quick, then only the upper coins will just come down. They will not fall. Okay, because they wanted to be there only. The lowermost has gone, but the uppermost, they want to be there only. So because of gravity, they'll just come down, but they will remain there only. But if you hit it a very slow velocity of striker, then it will fall down. What is the reason that it will fall down? Anyone? It will fall down if you hit with a very slow speed of the striker. Why? it was moving earlier also. Compare with the earlier situation, what has changed? If you move with a very slow striker, what is different now? Same situation was there earlier also, but now see the lowermost coin was exerting frictional force on the above coins. Okay, if you hit it very high velocity, lowermost coin got very little time to change the state of the above coins if you hit a very high velocity. But if you hit it very slow velocity, the lowermost coin got lot of time to exert friction and change the state of the above coin. Because it has got a lot of time, the friction has changed the state of the above coins, and so that is why the coins are falling down. Fine. All right. Now we'll be doing this topic again, by the way, in laws of motion. So we'll not get into too much of details right as of now. Tell me, uniform motion, uh, inertia of motion. Just tell me one or two examples, then we'll move ahead. Bus stops. Moving bus stops. What happens? Your lower part of the body, which is in contact with the bus, comes to rest as the bus stops, but the upper part of the body was free to move like that. It was moving forward only. Lower part of the body comes to rest. So your upper part will just move like that. Getting it? So that is the reason why you're wearing the seat belts also. In case of uh, some issue, something has hit, or you suddenly applied the brakes, your upper part of body will hit the front. So if you have a seat belt, then the lot lesser uh, you know damage will happen. Okay, somebody said people jumping from the moving bus. So this is a moving bus. Don't try this experiment. It's very dangerous. We're just theoretically telling here. Suppose the bus is moving with velocity v, and this is you. You have jumped off the road, and you have stopped. So which side you will fall? First or second? One or two. If you have suddenly jumped out of the bus and your feet are stuck, two, because your upper part of the body is actually moving forward. So if the lower part of the body comes to rest, upper part of the body will fall down. Suppose you don't want to fall down, then what do you have to do? Suppose you don't want to fall, then what is you need to run. Correct. The lower part of the body should also move. Getting it? So you'll not rotate. So if lower part of the body and the upper part of the body, if their speeds matches, then you'll be remaining straight like this and you're running. Fine. So if somebody is jumping out of moving vehicle, he has to run. Otherwise, he'll just fall because of inertia. So these are the natural behaviors which are there. And by the way, these laws which I'm talking about here, 3 laws of motion. First law we have already discussed. These laws are governed by the nature. Okay, so we'll not find out any exceptions there. So we'll assume there are no exceptions. Every mass on this planet has to follow these laws. Okay, these are the laws. Like Indian Constitution has certain laws. If you break the laws, police will come and arrest you. So most of the citizens are law abiding because of the force or because of whatever reason. Here, instead of police, nature is there. So there is no this thing. Every object has to follow these laws. Okay. So this is the first law of motion. We'll discuss it again when we do the laws of motion chapter. Now let us get into the second law of motion. Write down. Second law of motion. Now, just like first law of motion, suppose a child comes to you. In a layman's word, what you will tell? First law of motion, what it talks about. First law of motion talks about the behavior of an object, what objects wants to do. Second law of motion talks about what? What does it talks about? Anything that comes in your mind. There is no right or wrong answer. Getting it? It is nothing is right, nothing is wrong. It's all what you think. That is what I wanted to hear. That's all. How force applied related to change in speed? Okay, what is applied on object to make it move? Very good. Now, can you relate it to the first law? Whatever you studied in first law, okay, can you relate first law of motion and second law of motion? Whatever words you have used in the first law, can you use the same words in second law to explain? It will be much more crispier that way. No one? Okay, here's the thing, guys. If you don't want to change the state of an object, if you don't want to change the state of an object, do you need to apply any force? Do you need to apply any effort? Any effort needs to be applied if if you don't want an object to change its state. Suppose the person wants to watch mobile phone. In order to make sure the person watches mobile phone, do you have to make any effort? The person will watch the mobile phone, so you are not changing anything, so you'll continue to do that. You're not applying any effort here. Second law of motion tells you how much effort you should apply to change a certain amount of state of an object. If you don't want to change a state, no effort is required. But if you want to change the state, there's an effort that is required, and second law tells you how much effort. Okay, write down second law of motion tells how much effort is, see, I have not used words like force here. Okay, I'm using effort word to explain how much effort is required to change a given amount of state of an object. This is how you explain what the second law tells. Okay, so in physics, effort is formally referred as force. Okay, so going forward, whenever we talk about effort, we mean force. Fine, there should not be any ambiguity. Now, let us take few experiments and see how we can get the outcome or how much effort is required based on the experiment. We'll find out that. Okay. Now here, throughout this discussion, we are assuming mass is constant because today's topic, we are not going to change mass. So mass is constant is the assumption when we are discussing it right now. All right, so write down experiment number one. Experiment number one. Fine. You have, let's say, 1 gram of object and you have 1 kg of an object. Okay. This is moving with 2 meters per second. That is also moving with 2 meters per second. Fine. And both the objects you are stopping over here in delta t time. Okay, so the velocities are same, delta t is same. What is different is mass. You need to tell me where you need to apply more force or more effort. Tell me. Do you need to apply more effort in the heavier or the lighter one? Bigger object, heavier one, obvious, right? So this comes from the basic sense or common sense. Nobody can, prove you that you need to apply more effort here. This is what you feel, this is what you observe, and this is common across. So this tells us force is proportional to what? Force is proportional to m, or force is proportional to m square or m cube. Which one do you think is correct? This one or that one? Why first one? Why not second one? Why not second one? Why not force is proportional to m square? Okay, we don't know that. See, who has created the concept of force? The God has created, or we have created? Humans have created. Humans have created. We have created, right? What God has created, God or nature or whatever you may want to call it, they have given you certain observations, like this observation that we are talking about. The observation is what? Heavier the mass, more the effort. So whatever formula you take for the force must increase with the mass. You cannot say force is proportional to 1 by m. That will be against the nature's observation. Fine. And hence, it is up to me whether to take force proportional to m or m square or m cube or m to the power 5. I can take anything. Okay. And when it is up to me to define something like force, I will take the simplest possible case. And simplest possible case is force is proportional to m to the power 1. Okay. So we will assume this. Force increases. Force should increase with mass. That should not be breached. Okay. And it is up to me to which one I want to take. So I have taken the simplest one. Okay. This is coming from experiment number 1, guys. Now write down experiment number 2. Write down 1 gram. This is also 1 gram. Fine. This object is moving with 2 meter per second, and that object was moving with 10 meter per second. Okay. You have stopped both of them in delta t time. So amount of time taken to stop is same, masses are same, the velocities are different. So what I can tell here, force is proportional to what? Anyone? Force is proportional to what? V? Okay. That is wrong. You're saying that force is proportional to initial velocity. I have not introduced acceleration here. I have not discussed the acceleration. Why are you talking acceleration? Whatever is given in the experiment, use that. Change in velocity. Change in velocity. Because final velocity is 0, change in velocity is initial velocity. What if the second object final velocity was 9 meter per second? Then effort required here and there will be same. Change in velocity of second object will be 10 minus 9, 1 only. Sorry, 10 minus 8, 2 only. Above 1 is also 2. So the effort required will be same. Just because final velocity is 0, change in velocity is initial velocity. Okay. So in reality, when you formulate this thing, you need to be very careful. Force is proportional to how much velocity has been changed. Getting it? Now the final experiment, all of you write down. Experiment number 3 is this. You have 1 gram of object. You have 1 gram of object. Both of them moving with the same velocity, 10 meter per second. And this one, 10 meter per second. Okay. Fine. This one, you're stopping suddenly in delta t time. Okay. And this one, the second one, you are stopping by using a shock absorber or a spring kind of mechanism. So basically, this object will slowly reduce to, this object velocity will slowly reduce to 0. It'll take, let's say, 10 times delta t time. Here you're stopping by hand, here you're stopping by a spring. Where do you think more effort is required? First case or second? First case, right? So force should be proportional to what? Velocity is same, mass is same, delta T is different. So force is proportional to delta T. More is delta T, more is force. 1 by delta T. If time taken is less, force should be more, right? So force is proportional to 1 by delta T. Okay, so these are the common observations that everybody knows. We'll be using these three equations to create the formulation of the force. Okay, now tell me, if mass is 0, effort required will be 0 or not? It is almost 0 mass. Force will be 0. If change in velocity is 0, again force should be 0. And if you're taking infinite amount of time to stop an object, then also force should be 0. Okay, so if any of mass, delta V, or 1 by delta T, if any of these three becomes 0, effort should be 0. So that is why effort can be written as, or force can be written as, multiplication of these three quantities, so that if any of these three quantities becomes 0, force should become 0. Okay, so we can write, after combining all of that, we can say that force is proportional to m delta V by delta T. There will be a constant of proportionality also. So force is equal to K times M delta V by delta T. What is the value of K? K should be what? K is, we have to assume what is K. God, see, the thing is that many a times the value of F will be given to you and you have to find the acceleration. F is already given to you, 10 Newton, 100 Newton, things like that. Right now, my dear friends, you are defining force. Force is not given to you. You have to come up with an expression. Once you come up with the expression, then you have told the world that, listen, this is the expression, use this to identify all the forces. So you're deriving the expression for it. So either you take the value of K to be 1 or 100 or 1000, it doesn't matter. It will still be same. It can be counted as force only. If I say K is 100, the value of force will be 100 times mass into delta V by delta T. Nobody can argue against it because it is in line with the common observation. But then why to complicate our life, right? So we will keep the value of K to be 1. So value of K is assumed to be 1. Fine. So it will be M delta V by delta T. What is delta V by delta T? Anyone? Acceleration. So this is F equals to ma. Fine. So F, the force is a vector quantity, acceleration is also a vector quantity. So this is the Newton's second law equation for the case when mass is constant. Force is equal to mass time acceleration. Fine. So I hope all of you have understood the second law of motion, and this quantifies the force with mass and acceleration. There's no point of K. Okay, so from proportionality you have put an equal to sign. Understood, Aditya? See, the thing is that force is not given to you. Your first time defining force. Who told you 1 meter is this much? Who told you 1 meter is this much? You've assumed it, right? Who told you that the mass of this is about 1 kg? Because you've already assumed what is 1 kg. So compared to that, this is also 1 kg. Who told you what is 1 second? Everything is assumed. Yes or no? So Newton has given us a window through which you can see the world and understand what is going on. And this is the most important equation of the Newtonian physics framework. Is it clear? No, Anushka, this is not that kid. No, no, no. This is not that. All right, guys. So this is the second law of motion. And let me tell you, mark my words, it looks very cute, very simple, but this formula creates a lot of trouble in class 11th. Okay, you'll see that when you solve problems. But right now we are not completely using this. We'll be doing it in laws of motion chapter. Okay, write down third law of motion. Third law of motion. First law tells us the behavior of an object. Second law tells us how much effort is required to change a given state of an object, or what will happen to an object if you apply force. What does third law of motion tells us? What it is about? Anyone? What it tries to tell us? How object, okay, gives it back, karma. Sure. The effects objects have on each other. Great. So all of you are correct in a way. Very good. So basically, third law of motion tells what will happen. By the way, third law of motion is the law where almost everyone makes silly errors, and you'll see. So this is what will happen to the object, who is applying the force. Second law of motion tells us what will happen to the object on which force is applied. Third law of motion will tell us what will happen to an object who is applying the force. When I say objects, living being, non-living being, everything is counted. Okay, don't think that object means non-living thing only. Okay, so suppose I have, sorry about that. Suppose I have two objects, object A and object B. Two objects are there. These two objects are applying force. Okay, object A is applying force on object B. Let's say object A is applying force on object B like this. So what will happen to A? This A is applying. How it is applying? They can be magnets, they can be charges. I mean, they can be direct contact. Let's not discuss how they are applying force. Okay, if A is applying B, the force in that direction, how B will, what B will do? What B will do? Anyone? Apply, exert force in opposite direction. Okay, correct. B will apply an equal and opposite force on A like this. Okay, all of you getting it? By the way, some of you might be willing to state that every action, you have been mugging this up for a couple of years now, every action has an equal and opposite reaction. Okay, when we are talking about action, we mean force. So on B, A's action is F. On A, B's reaction is F. Fine, equal and opposite. Now all of you listen to this very carefully now. If there is a force in this universe, first of all, there is only one verse. Okay, one universe is there. We are not talking about multiverses or multiple universes. Only one universe. If there is a force in this universe, some object or someone in this universe only will be applying that force or not. if there's a force in this universe, some object or some person in the universe only will be applying that force, because there is nothing outside the universe. Are you guys understanding what I'm trying to say? If there's a force in this universe, if there's a force in this universe, some object in this universe only will be applying that force. Clear? So on that object who is applying the force, there will be equal and opposite reaction. Suppose A is that object who is applying that force. So there is an equal and opposite reaction on F. So can I say every force in this universe has a pair which is in opposite direction in the universe itself? Can I say that? Please type in yes or no. Every force that you see in the universe has a pair in opposite direction in the universe only. Clear? This is the most important thing about the third law. Okay, so every force, or in a crispier manner we can write forces exists in pairs. This is the crux of third law of motion. Forces exist in pairs. Fine. If you see a force when you're solving any question in mechanics for rest of your life, whenever you're doing it and you apply a force, ask yourself, where is a pair of this force? Where is a pair of this? You're applying third law there to identify the pair of that force. If you're not able to answer that question, that where is a pair of that force, you are doing it wrong and you'll get wrong answer. Getting it? It means you are not in control. So just leave it. Getting it? So whenever you see a force, ask yourself, where is the pair of that force? Period. Okay? So let me just ask you a common scenario and tell me where is a pair. Like I think I think 2 classes back we have done projectile motion. So on projectile, what is a force acting on a projectile? Tell me. On projectile, gravity force is acting. How much? How much? mg. Mg is acting, right? Where is a pair of mg? Pair of mg is where? Projectile, mg is acting. Where is the pair of that mg force? Because every force should have a pair. So where it is? Correct. Very good. It is not a normal force. Pair is not that. Who is applying mg on the object? Who is applying mg? mg is applied by the earth. It's like B is earth and A is the object. So earth will get pulled up by an equal and opposite force by the object mg. Keep it very, very simple. Things are very simple. Getting it? So this is the pair. On earth, mg applied in the upward direction. Getting it? Now, just tell me few examples where you observe third law of motion in your day-to-day life. Just take random examples. Most common thing you do, rowing a boat. What? Where you row the boat? Walking. Walking. When you walk, which direction you push? Which direction you push the floor? Backwards, right? And you are moving forward because of when you push the floor backwards, floor pushes you forward and you're able to walk. And that force is friction. If friction is not there, floor will not be able to push you forward direction. Okay. When you're jumping from the floor, which direction you push the floor? You push the floor down, but you're moving up. Why? Why you move up? You're pushing it down because you are pushing floor down. You're not pushing yourself down. When you push the floor down, floor pushes you up and you jump. That a pair of force acting on you. When you're swimming forward, which direction you push the water? Forward or backward if you want to move forward? You push the water back, then only you're moving forward. The reason? When you push the water back, water pushes you forward from Newton's third law of motion. Getting it? So there are various examples. Almost everywhere Newton's third law of motion is there, and sadly, almost every other student makes mistake in applying third law of motion because students consider second law of motion is everything. They don't pay attention to third law of motion. And the person who is setting the paper knows that you have not studied third law of motion properly. So he will set a paper in such a way that you make error in third law. All right, so these are the three laws of motion. This is the behavior of the object, how object will behave. Now we will take the forces, one by one we'll take forces and study the behavior of the forces. Okay, once we are done with the behavior of forces, after that, we'll just take the problems and see how to draw the free body diagram. Okay. All right, guys. So write down the first and foremost, the most common force. Okay. What is the most common force? By the way, why don't you tell me all the forces which you guys know? Can you tell me that first? Whatever forces you know, just tell me. Okay. Gravitation, mechanical, normal, what else? Weak and strong, okay. Then contact, centrifugal, magnetic. Centripetal, centrifugal. What else? Electrical, okay. Nuclear, weak nuclear, strong nuclear. Electromagnetic. Is that it? Okay, gravitational again. All right, so thermal force, friction. Okay, now hold on, listen here. So broadly, whatever examples that you have given, you can see that the examples can be broadly classified into two types of the forces: contact forces and non-contact forces. The forces that require contact and the forces that do not require any contact. Okay, so we'll first talk about forces that require contact. So please start typing. The first one I'll write down, normal. We'll discuss it anyways. Any other force that you know which requires contact? Yes, friction. What else? Okay, people are saying mechanical force. What do you mean by mechanical force? Mechanical force is not a type of force, as in it is a category of force. It is not a force. Normal force can be mechanical. Friction can be mechanical. It's a category. Getting it? So that's not a force. Normal friction. What else comes in your mind? Tell me. What else? Anything else? No one. Array, normal friction. What about tension? Have you heard of tension? Tension, have you heard? That is because of string. String can apply force, right? And then what? One very important force, our day-to-day life, we are using in vehicles everywhere. Air resistance, drag. See, we are not discussing that. Okay, the drag is like a friction only. You can say you can categorize under that. Drag comes under normal and friction. We are talking about solids here, solid objects. Torque is not a force. Torque is not a force. It is the effect of force, and it has a rotating effect. That is different. Normal will discuss what it is. Don't worry about it. Can you recollect any other force other than 3 that is written? No one? Muscular is not something. Muscular force is generated, which is electrostatic in nature. So that is not. So what I mean to say here is elastic force. Elasticity creates force. Okay. So your muscular force could be generating tension or elastic in nature. Fine. It can be frictional also. Elastic, they are generated usually from the spring or rubber band or anything else as well. So these are the 4 contact forces. There are no other contact forces other than these. Okay. So don't get confused. Non-contact forces. Gravitation. List down. Gravitation is one. Electric, magnetic. Pradyan, hold on. We'll discuss it. Magnetic. Then electric is electrostatic. Fine. Then the weak and strong. These are called as nuclear forces. There are 2 kinds of nuclear forces, weak and strong. Okay. Getting it? In class 11th, our focus is what? What are the forces which are our focus? Normal, we'll discuss it. Friction, tension, elastic, and gravitation. This we will study in class 12th, electric and magnetic in class 12th. This, if you have to do PhD, to study it. Fine. So in class 11th, we are going to only focus on 5 forces. Only 5. Normal, friction, tension, elastic, and gravitation. Out of 5, only 1 is non-contact, that is gravitational. Fine. Any doubts till now? Anything? Anyone? Anyone has any doubts? No doubts? Okay. So, by the way, I should tell you this, that normal, friction, tension, and elastic, they are all electrostatic in nature. Okay, but we are not assuming them to be electrostatics. We are studying it as a separate kind of force. In nature, only 4 fundamental forces are there. Okay, but we are studying it as if they are the separate forces. Okay, so let's take one by one these forces and study their behavior. First one is gravitation. Let us study a little bit about gravitation. Gravitational force. Today we are going to assume that we are dealing with the objects that are kept close to the Earth's surface. If I'm close to the Earth's surface, how does Earth looks to me? How does it look like? Look like a plane, look like flat surface. Okay, so hence it will look like a flat surface. So don't debate on that, sir, Earth is sphere, so why you're taking a flat surface. You're dealing with only situations in which objects are very close to Earth's surface, and usually that is what happens. That is what usually the scenario is. Okay, so direction of force, write down. Which direction do you think the force, gravitational force will be? What should be the direction of force? Vertically? Vertically down. Okay, there is no exception to it. The direction of gravitational force on the object is vertically down. Okay, no matter where, how, or what object is doing, there will always be a gravitational force vertically down. So if you have to show the gravitational force on an object, you have to simply draw an arrow like this. This will show the direction of the force. Any doubts to anyone with respect to the direction? Isn't it straightforward? Okay, magnitude is how much? Anyone? Direction is vertically down. Magnitude is 9.8 or mg or gmm by r square. Gmm by r square or mg. It is mg, and you might know or don't know the value of g. Small g is g into mass of earth divided by radius of earth whole square, which comes out to be 9.8 meter per second square. Okay, so inside this g, this is what is hidden, and they assume that when you write mg, you are assuming distance between the center of the earth and the object is radius of the earth only, as if the object is very close to the earth's surface. So when you are showing the gravitational force in a free body diagram, listen here, when you're showing free body diagram, mg, you need to write like this and show mg like this. So just next to the arrow, you write down mg. If m is 2, you write down 2g. M is 5, you write down 5g. Things like that. Okay, so this is about the gravitational force, how it is applied, and it is the first force you should show in your free body diagram, because it's very simple. All the masses will have this force. So first thing you should do in any free body diagram is to represent mg force, period. After that, you think what to do. First thing is draw mg. Next up is write down, many of you have asked about the normal force, so let us discuss that. Write down. Normal force. Suppose, let's say I take an example of a table. Table like this. Okay. An object of mass m is kept on it. What is the force acting on this mass? What is the first force that you draw? Mg, right? It is Mg. Okay. Then why it is not moving down? Mg is a force. It should move down. Who is preventing its motion? Table is preventing its motion. Correct? Now how it is preventing the motion? How table is preventing its motion? What table is doing? Table is applying a force to prevent its motion. It is not coming from third law. Remember that. Table is applying a different force, which is not the pair of mg. Pair of mg is on the earth. On the earth, pair of mg is. We have discussed it already. But the object doesn't move because on the object, my dear friends, there is another force applied by the table n. Getting it? So where is a pair of n? Where is a pair of n? Anyone? Pair of mg is on the earth. Pair of n is what? Pair of n. All of you find out pair of n, where it is. Which direction and where it is. Direction also. Direction. Correct. Correct. It is downward direction on the table, which is n. Getting it? It is not mg. It is equal to mg right now, but in many scenarios, n is not equal to mg. Getting it? So this is the pair of normal force. And if table is weak, if table is very weak, then the pair of n, then the pair of the normal reaction on the table, which is this, will break it. So if you are keeping the mass on a table made up of paper, a very, very fragile table on which you keep a mass, table will collapse. The reason? Because normal reaction on the table is acting down. So if table is not strong enough, it will collapse. Getting it? So when you're sitting on a chair, when you sit on a chair, do you feel that you're exerting force on the chair? Do you feel that? Right? That is the normal reaction pair. Do you also feel the chair is exerting force on you? Do you also feel that? That is the normal reaction. Just like here, normal reaction is on the mass. Okay. Do you think it is gravity? Do you think the force which you are applying on the chair or chair applies on you, is that gravity? All of you please type in. It has nothing to do with gravity. It may be sometime equal to gravity force, but they are not same. Most of the time they will be different. All of you clear about this example? Please tell me yes or no. or you can ask any doubts, because this is very important, very, very important. Typing yes or no. Have you understood? If they are different, won't there be a motion in the body? Yes. For example, when you are moving in a lift, when the lift is moving up, don't you feel that on your legs more force is being applied by the lift? Normal reaction from the lift has increased when the lift is going up. Have you ever felt that? And when the lift is going down, you feel light, because normal reaction on your feet is less than mg. If lift starts accelerating with 9.8, normal reaction will become 0. You'll feel weightless. Okay, so when you measure your weight on the weighing scale, you're measuring the amount of normal reaction only. Okay, and if you're moving when you're measuring your weights will be different. Try putting the weighing scale on a moving lift and then measure your weight. You'll see that when lift is going up, your weight measurement will be more. When lift is going down, your weight measurement will be lesser, because weighing scale reacts to normal reaction. It doesn't react to gravity. Done? Whatever doubts are, please type in quickly. I'll move ahead. So normal reaction, type in your doubts. Don't say that I have doubt and then I have to wait for 2 minutes for you to type it out. Yeah, you can unmute. Normal reaction is perpendicular to the surface of contact. Write down. Why are not asking doubt? Should I wait for? Tell me.
You gave the lift example, like when we're moving down, the weight decreases. That's what you said. So, but when we're accelerating downwards, should the force on the legs be more and then like the weight increases?
No. No, it is not that. Just check it once more. When the lift is going down, you'll feel the force on your feet is lesser. Okay. When lift is going up, force on your feet will be more. Just check it once.
But why, sir?
Because normal reaction will be reduced. I'll just tell you one example here. Suppose the table is moving down with acceleration of a down. Okay. Newton's second law says net force, which is mg minus n, should be equal to m into a. So normal reaction will be what? M into g minus a. So normal reaction is no longer equal to mg. It is m into g minus a. It comes from the second law of motion. All right. So we'll be doing it. Don't worry about it. But then this is what happens when something moves. Normal reaction will change, because mg minus n is m into a. Understood? Anushka is saying, okay, sir. When she has to say, okay, she is typing. All right. Write down, all of you. Normal reaction is applied perpendicular to the surface of contact. Fine. Now, can I say normal reaction? Tell me one thing. Normal reaction should pull or push? What type of force it will be? Can I say it is always push? Normal reaction is always push. Can I say that? Is always a push force. Have you ever felt that the floor on which you are walking is pulling you down? Or it is always a push? Type it out, all of you. Is it always a push, Anushka? In a lift, while going down, it is a pull. Oh, it is a push only there as well, but it is a lesser amount of push. Okay, when it is going down, lift when it is going down. It will never happen that uh, an object is just, the floor is getting hold of your legs and pulling you down. If lift suddenly starts moving very fast down, you'll be in air. You'll be in air. You lose contact from the lift itself. Normal reaction becomes zero. You'll be weightless if lift is going extremely fast. Fine. But normal reaction can never ever pull you down, can never hold your legs and pull you down. Getting it? It is always push. It always pushes you. It always pushes you away from the surface. Getting it? It's always a push. Normal reaction is represented by N. Okay. Its value, write down. Its value can be anywhere between 0 and infinity. How you find the value? By using second law. If you use second law, you'll be able to find the value of normal reaction. Okay, so 2 points. Normal reaction is applied perpendicular to the surface of contact. We have seen how to draw perpendicular to the wedge, right? Along that direction only normal reaction will be applied. Okay, and normal reaction always a push force. Clear to everyone? Any doubts to anyone? No doubts. Okay, fine. So let's draw some free body diagrams where we represent the forces by arrows. Okay. So free body diagram, when you draw, make sure you are following these basic steps. Step number 1. Choose an object for which you're drawing free body diagram. Okay. All right. And when you're choosing the object, choosing means you need to redraw the object. Redraw the object alone. Do not change the orientation. Do not change don't change the orientation of object. What I mean to say is that if, let us say, this is the case, if on an inclined plane there is a mass kept like this, I want to draw a free body diagram of this mass. You should take mass as it is like that and draw it over here. And then you show the forces, mg down, normal direction like this, whatever. Don't rotate the mass and make it horizontal like that. This you should not do. Keep the orientation like that only so that angles are visible. This is what it is. So this is the first step. Step number 2. Choose the x and y coordinates. X and y coordinates. Why not z coordinate also? Anyone? Why not x, y, z? All three. Why not all three? Anyone? Because the problems we are taking are two-dimensional in nature. That's the only thing. Okay? They're two-dimensional in nature. Step number 3. Draw forces by using arrows. Arrows should be used to draw the forces. Direction of the force is the direction of the arrowhead. Okay, the arrows must touch the object. Touch the object. If arrow touch the object, it means the force is acting on that object. Fine. And also find angles of all forces with x and y axis. Fine. Step number 4 is take components. This is what you have studied earlier also. Components will never leave you. Okay. Take components of force vectors along x and along y axis. This is what we are going to do today and nothing else. Just read it once. All of you read it once. All of you. This is what we'll do. We'll not solve any equation. We are not writing any this thing. We are just doing this. That's all. Done? Done. Before we start drawing the free body diagram, is there any doubts anyone having? Please type it. Don't hesitate. Type it out. No one has any doubts? Okay, fine. Let us take let's take few examples here and we'll draw the diagram. All of you draw the free body diagram of both the masses. Sorry, both the problems. There is only one mass in question number 1. For this, we draw free body diagram. Here you have two masses. This is 10 kg and let's say this is 50 kg. Okay, both 10 kg and 50 kg can move. Draw the free body diagram for both. Are you done with the first one? Type in yes or no. Have you done with the first one? Yes. Okay. Gurman, Kshitij, Ansh are done. Others? Oro is done. Aditya. Aditi, Arabi. Sanmukh. Anushka. Okay. Done. Anushka, you did not get it? What is the trouble? mg force over here and normal force over there. The pair of normal reaction is on the floor like this. This is the free body diagram. Okay. Now free body diagram of this case. Second one also, I am assuming all of you have done it. Second one, 10 kg block. mg acting like this. Where the normal reaction will be, all of you? M is 10, so I'll write it as 10g. Normal reaction will act where? Which direction? Perpendicular to the surface. Perpendicular to the surface, like this. Correct. Like that. This is the normal reaction. How do you want to keep your x and y axis? Where is your x and y axis? You keep it like this, x and y. Getting it? So with x-axis and with the y-axis, this angle is how much? Tell me. If this is theta, this angle is also theta. You can check. There is 90 minus theta, so this angle becomes theta. Okay. So this component of mg is mg cos of theta, and that component of mg is mg sine of theta. So you will encounter these inclined plane types many a times. Getting it? So always remember, along the incline, it is mg sine theta. Okay. Whenever you have a block kept on an inclined plane, along the inclined plane, it is mg sine theta. It will help you unnecessarily. You will not think in that. How many of you got free body diagram of the second block? Correct. Okay. Fine. Now I'll be drawing free body diagram of this incline. First thing is, no, friction I haven't taught. Friction is not there. Friction is not there. Along the incline means in the direction of hypotenuse, like this, is my x-axis. This is 50g, one force, any other force on this. Normal, like this. This is, let's say, a new normal, let's say N1. The pair of normal force, where is a pair of this normal force? Its pair will act in opposite direction like this. Don't write minus n, just change the direction of an arrow n. This is applied by the inclined plane. So on inclined plane, n is applied in opposite direction. Okay, this completes the free body diagram of the incline as well. All right. Now you can take component of n also. Could you please draw a triangle from which you take components? Triangle. There is no triangle. See, this is mg. This angle is theta. So if you have to find the component of a vector along a line that makes theta degree, the component is mg cos theta. So along this angle is theta, mg cos theta. Okay, keep it simple. Component of a vector in a direction that makes angle theta is vector times cos theta. Okay. Now xy coordinate for this block is like that. For the wedge, you can have new x and y coordinate. Okay, this is something new. XY coordinate for all the masses need not be same. You can have a different XY coordinate. So here you take component of normal direction like this and like that. Getting it? Any doubts? This angle is theta. So this is n cos theta and this is n sin theta. So I'll just write it down here about the x and y axis. So different masses can have different x and y axis. Depending on how the mass is, you can have different x and y axis. So horizontal and vertical x and y axis makes more sense in case of inclined plane, because normal direction and mg are along the vertical line. Clear, right? All of you clear? I'll go to the next question. Do the first question first and let me know once you're done. You need to draw a free body diagram for both 1 kg and 2 kg. Okay. Oro is done. Others? Done for 1 kg or done for problem number 1? Problem 1 done. Very good. So shall we discuss it? Okay, listen here, all of you. We are discussing problem number 1. Don't start solving 2. There is no competition here. No points for getting it first. Most of the time, if you are first, you are wrong also. On 1 kg, there is 1g down and there is a normal reaction N1. Okay, this is 1 kg. 2 kg, I'll draw right below like that. This 2 kg. On 2 kg, there will be 2g force down. There will be a normal reaction from here. Let's call it as N1. What else? What else is acting on 2 kg? There is 1 kg and that is 2 kg. All of you please type out what is a missing force in 2 kg. normal force from ground. There is this normal force ground. This is N1. Correct. The pair of, okay, this I am writing N1 kya? N. The pair of N from the upper body to the lower one. N1. Sorry, N only. N. This is the answer for the first. We are not finding the values of anything. Today's session is only to draw the diagram. That's all. Tell me, does this make sense? Any doubts in this diagram, in this freebird diagram? Anyone has any doubt? Please feel free to ask doubts. I'll not take your names. Don't worry about it. Whatever doubts you have, please type it. mg from the upper body. Acha, from the upper body, is mg is applied on the lower body or normal reaction is applied on the lower body? All of you answer. mg is what? mg is the force earth applies. Earth applies on 1 kg. Okay. Earth applies on 1 kg a force of 1g. What 1 kg applies on 2 kg is normal reaction. Clear? All right. What about downward force by 2 kg on force? On the floor. Yeah, that is. Yeah, then I have to draw the floor also. I haven't drawn the floor. So this is the floor on which the 2 kg block has been kept. So on this, what force is applied? All of you tell me. What is the force on this floor? N1. The pair of N1 will be on the floor. Like this. Okay, N1 pair of N1. N pair of N. 1G and 2G pair I am not drawing. Because in order to draw pair of 1G and 2G, I need to draw Earth. So this is Earth. 1G pair is this and 2G pair is this. But usually we don't represent Earth. So don't bother about drawing the pair of gravity force. All right, guys, good that you are asking so many doubts. You must keep on asking a lot of doubts. Don't get embarrassed or anything about you asking silliest of the doubt. Okay, that's the last thing that you should be bothered about. Draw the freebird diagram of this question. There's a sphere and there's a cone. The cone is getting pushed. The cone is getting pushed from the left hand side. It in turn pushes the sphere against the wall. Draw the freebird diagram. Take the mass of the sphere as small m. Take this angle as theta, not 30 degree. This is also theta. It's a cone. Let me know as soon as you're done. Okay, Kshitij is done. Hope Kshitij, you're not making silly errors. Okay, Anusha is done. No, Kshitij, you're not trying. You're trying to finish it first. That's what you're trying. You have to be more careful. All right, so let us do this now. First, we will solve for the sphere. Okay, let's say this is the sphere. Okay, I need to draw the vertical line which represents the wall, and this represents the surface of the cone. Okay, this angle is theta. The first force that we should draw always is the gravity, like that. This is gravity mg, which now tell me, will there be a normal reaction from the wall, and in which direction if it is? Direction horizontal. The normal to the vertical is horizontal. It will pass through the center or not? Normal, this vertical line is tangent to the sphere. So when you draw a normal, it passes through the center. Okay. Is that it? Is there anything that I'm missing here? This is, let's say, N1. Anything else? What is F? On which block F is applied? On cone or on small m? Force by the cone. What is that? Force by the cone is what? Normal reaction. Normal reaction. Correct. So there will be a normal reaction. Will that also pass through the center of the cone, center of the sphere only? Will it be like this? Center of the sphere only will it pass? Correct. Let's call it as N2. Fine. Okay. How much is this angle? Anyone? This angle? How much it is? Do a little bit of geometry. Find out what is that angle. Do it, all of you. How much is that angle? This is 90 degree on which there is a line like this. What is that angle? 90 minus theta. All of you getting that? This is 90 minus theta. So now you can take the component of N2. N1 is horizontal, Mg is down. So just take component of N2. This is N2 sine theta and vertical is N2 cos theta. That's all. Fine. So this is the free body diagram of the sphere. For the cone, if I take cone like this only here itself, for the cone, F will be applied on the cone. Achha, by the way, when I apply F on the cone, does that affect the sphere also or not? Will sphere should get affected or not? It should get affected, but there is no F on the sphere. How it is getting affected? Anyone? When I'm applying force F, how it is affecting a sphere? As in, the F is applied on the cone, not on the sphere, right? Then how it is getting affected? When you are applying force F, the value of normal reaction will increase. The N2 will increase automatically. Okay, so indirectly F is increasing the value of normal reaction. Fine. Now let's do it for the cone. So there will be mg. This is mg. What else? There will be normal reaction from the floor N3. Sir, I got kicked out of the meeting. You are still on the meeting. That's why you're able to type in. Okay, now tell me, is there any other force? Okay, I haven't found 90 minus theta. Everybody told 90 minus theta. You can use little bit of geometry here. Okay, this is 90 degree. Then this angle is theta. This is also theta. So this is right angle triangle. So that is 90 minus theta, like that. Just do it your own. Geometry should be done your own. If somebody explains you get the answer, but you don't understand how to arrive at it. So best is you do it your own. It is simple. You'll get it. Now tell me, is there anything that I'm missing here? Normal from the, not circle, the sphere component. This is N2, like this. Okay, this is how you draw the diagram. Then you take the component of N2 like this and like that. Okay, find out the angles and take components. Clear. We'll go to the next up. Why not? Why N2 in other direction? What not in other direction? What do you mean? Why N2 in other direction? Because it's pair, na? N2 on sphere is this way. So sphere will create the reaction pair in opposite direction. Newton's third law. Wants to find component. No. I know what he wants. I understand Oro better. Fine. So let us see what we have next. This one. All of you do this. This is the last question before we take a break. After this, we'll take a break. FBD for both A and the plank. The inclined plane also. Inclined plane is massless. There is no mass. Let me know once you're done. Oro is done. Others? Kshitij done. Okay, many are done. Let us draw the free body diagram of A. This is, let's say, having mass M. There will be mg like that, there will be normal reaction perpendicular to the plane. Anything that I'm missing, let's say N1. Is that it? Anything else? Any other force? There is one more reaction, normal reaction from that. It has two supports, na? Every contact, write it down, every contact automatically implies normal reaction. In fact, in physics, contact means normal reaction. If normal reaction is zero, it means contact is not there. Many times you'll be solving problems later on that you need to find conditions when object loses the contact from the surface. The condition is when normal reaction becomes zero. Okay. If there's a contact, there has to be normal reaction. It's that simple. Okay. And keep it simple that way only. So we'll take component of mg. So along the incline, what is this component? How much it is? This component is what? Mg sine theta. You need to remember it. Mg sine theta. Don't try to find components every time you find the angles and then component. Along the incline, always mg sine theta perpendicular to incline mg cos theta. Just keep it as a thumb rule so that you don't need to do it again and again. So this is the free body diagram of the small m. And if you want to draw the free body diagram of the Planck, Planck is actually supported on the ground as well. We are not showing that ground force. We are only showing the normal reaction pair. Achha, by the way, the Planck doesn't come alone. There is a support also. This is an integral part of the Planck. So the pair of N1 like this, pair of N2 like that. So this is N1, this is N2. Okay. So all of you understood this? Anyone has any doubts? Anyone has any doubts? All of you understood? What about normal force on the ground? Yeah, I'm not drawing the forces from the ground on the Planck. Okay, I'm not doing that. It's part of ground only, I'm saying. Mass of Planck is 0. I told na initially. Is it clear to everyone? Any other doubt? All right, no doubts. So we will take a 15 minutes break. Right now it is 6:03. We will meet after 15 minutes sharp at 6:18. Come back on time and we will continue. Right now we have just solved basic. Okay, basics we have done. When you come back, we will get introduced to another force, tension, and then we'll solve more questions. This is break. Bye for now. All right, friends. Hope all of you have come back. All right. So we will continue now. And we have only studied about the two forces till now. And the forces that we have studied till now, they are gravitation and normal direction only. So we have taken the questions also from only these two forces. So let us talk about the third force so that we take up the another set of questions, and that is tension. Write down. So as we have already discussed, string causes the tension force. Fine. So string causes this force. All right. And throughout the discussion, whenever we have, whenever we talk about the tension force, there are few assumptions. Okay. What are they? The assumptions, write down. String is massless. String has no friction. String is frictionless. And string is inextensible. String cannot get extended. Okay, it can't get extended. So what does it mean? It has a fixed length. We have used this phenomena, fixed length, right, to understand the constant motion also with respect to the string. So these are the assumptions. Based on these assumptions, we'll be talking about the tension force. Fine. So let's take the most simple scenario here. A block is hanging with a string like this. A block is hanging like this. Right? So tension force, it is represented by T, represented by letter capital T. This is what the convention is. Just like normal reaction, people use capital N. For tension, we use capital T. Fine. Now tell me, can you push any object by using string? Is it possible to push an object by using a string which has these three characteristics? Can I attach an object with a string and push by using string? I cannot, right? So string can never push. Getting it? So tension is a pull force. It is a pull force. It's a pull. If there's a tension in the string, it will always pull. Pull is like pulling towards itself. Push is pushing away from itself. So floor pushes away from the floor. String pulls towards itself. Fine. So this is what the difference is between push and pull. Now, which direction the string will pull? What is the direction of pull? Anyone? direction of pull, direction of tension is, write down, along the string. Along the string, whichever direction the string is going, along that direction it will pull. Pulling can be in various directions. It will be like this, like that, like that, like this. Which direction the pull is? The pull is along the string. So keep that thing in mind. Now let's draw the diagram for the capital M only. This is capital M. There will be mg force down. Why it is not moving down still? Because the string is pulling up, right? String is pulling up with a force of tension T. Getting it? This point A is getting pulled by point B on the string. Okay, so if you draw the free body diagram of the string, if you draw the free body diagram of the string, all of you draw this. We are not calculating any force, Ansh. We are just drawing the diagram. Today's topic is drawing diagram, not to calculate the value. This is A. On B, which direction the force will be? Tell me. This is string, the remaining string. Which direction the force will be on B? B is pulling A with capital T. So what will happen to B? What will happen to B? All of you. On B, equal and opposite reaction. T is downwards. T is downwards. B is pulling A with T. A is pulling B with T. Getting it? A is pulling towards itself. B is pulling towards itself. So at a particular location, both sides you'll see the tension, upward as well as downward. Downward on the above points, upwards on the lower points. Okay, now let's cut this string a bit from here. Let's cut it. Now tell me, if there's this remaining string here and this much string, if I keep it here, this is the string from here to here, point 1 to 2, and this is 3. This is 1 to 2 string, and this one is from 2 to 3. Okay, I know at point 3 there's a tension T like this. Will there be a force on 2? Tell me. I have cut the string. I'm drawing free body diagram of 2 to 3 only, from here to here. On point 3, tension is T down. So this string is at rest. So there has to be a tension upward force also, so that net force is 0. Getting it? And that is why on 2, there will be a reaction of that tension like that. So what we have done just now, we are saying that tension force is present throughout the string. It is not present only at the end of the string. Everywhere tension is there. So when you stretch something, the stretching happens not just at the ends. The stretching force is throughout the string. Yes or no? All of you understand this? So what I have said is tension will be same throughout the string. Is there any doubt in this, all of you? Doesn't matter the length, because anyway it is massless, frictionless, can't get extended. So it is like, if this is string, if I pull it from both sides, okay, even the point in between will feel the stretch. It is not that only this point and that point feels the stretch. That is what I'm trying to say, that tension will be there throughout the string. All of you understand this? Type in yes or no. Quickly do that. Otherwise, I keep on waiting unnecessarily. Fine. All right. Great. So there is a thumb rule, guys. The thumb rule is whenever you're dealing with the string, this is like thumb rule. Same string, same tension. Throughout the string, if there's one string, throughout the string, there will be tension at each and every point. There will be tension. Okay. So this is a rule that you have to follow. Okay. Now, whenever we are dealing with the string, one part which is integral that comes along with string is pulley. Okay. Sir, what if the object is in the middle of the string? So are you telling me this is a situation, this one? Is this the situation you're talking about? This is M1, this is M2. Okay, so you can see there are two strings, one string and two string. So let us draw the free body diagram of M2 first. So M2G downwards, and let's say tension on this string 1, this is string 2, tension on due to string 1 is T1. So this is M2. Okay. Now let's draw the free body diagram of M1. This is M1. Okay. There will be M1G and there will be string from tension 2. Sorry, string 2. So let's call it as T2. Tell me, is this correct or something is missing? Something is missing or not? Tension from S1 on what? This is right. This is the tension from S1. On M1, the string will apply force T1. String will pull anything that it is attached to with tension force. And same string is same tension. On M2 and M1, string 1 is same. So T1 on M2 as well as on M1. But M1 is getting pulled down because string is down. And M2 is getting pulled up by the same tension because it is same string. Understood, Anusha? Okay, now let's talk about pulley. What pulleys are used for? The function of pulleys are these. Write down pulley helps in changing the direction of tension without affecting the magnitude. Okay, this is the first function. Second is actually force multiplier that we are not bothered about right now. Force multiplier we'll discuss later on when we'll be doing laws of motion chapter. Our focus is this. Okay, and there are assumptions with respect to pulley as well. We are dealing with the ideal pulleys. Ideal pulley. Until unless it is stated, we will assume it is ideal pulley. It means the pulleys are massless and frictionless. Do you know if pulley and string, they are massless, then pulley will never rotate. The string will just slide over it because there has to be some force which rotates it. That comes from friction only. If friction is not there, this pen, even if it is trying to rotate, even if it can rotate like that, If friction is not there, my fingers will just slide over it. It will never rotate. So ideal pulleys never rotate. There's no torque on ideal pulleys. Anyways, coming back. So let's take an example of how pulley works. Let's take this example. Let's have a single pulley. This is a single pulley. This one. All of you, please draw the free body diagram of M1, M2, and pulley. All of you, try this. This is very important, guys. If you understand today's session completely, you will be very much ahead of everybody else. Okay, try doing it. Let me know once you're done. Oro is done. Gurman. Okay. Fine. Many of you have done. Let's take M1. There will be M1G like this and T. That. This is M1. Okay. M2. There's M2. So it will have M2G, and this tension will be same or not? Both are same tension or not? Same? Yes. Same string, same tension. It is a single string, so both will have same tension. Now pulley. This is pulley. Since it is the ideal pulley, it has no mass. So it will have tensions will pull it down. T and T. Same tension, right? Tension. And there is one more string at the top that is different string. So it will have T1 tension. This is what I wanted to see. Okay. Let's take another example. Draw the free body diagram of all the masses and all the pulleys, M1, M2, and M3. If there is any doubt, please type in immediately. Don't hold back your doubts. Okay. What about M into A? M into A is not force. M into A is the outcome of the force. When you eat food, outcome is energy. Energy is not your food. We are not showing M into A. We are showing only forces. Let me know once you are done. Done. Aditya is done. Done. Others? Kshitij, Oro, Gurman. Done. Okay, I'll do it now. If the pulley is massless, then why would there be tension acting on it? Why not? You're saying massless object doesn't have force. Massless object can also experience force, right? There is no law stating that if there is lesser mass, the force should be lesser. Okay? So M1 is having M1G like this. It will have, let's say, see, I'm drawing favor diagram on the diagram itself because the space is lesser, but otherwise you need to draw it separately. This is T1. So tension over here is T1 because it is the same string attached to the pulley. Okay, but over here tensions will be different. This will be M2G. This is T2. This is T2. This is M3G. Now let's call it as P1 and P2 pulley. So first I'll draw for the P1. On P1, let's call it as T3. This is T1. This is T1. Okay, this is pulley P1 and pulley P2. Pulley P2 will have tension T1 like this and T2 and T2 like that. Tell me, any one of you have any doubts? Type in. Okay, this is very, very important. Probably this is the most important part of whatever we are doing today. Okay, so if there is iota of your doubt, please ask. Type in yes or no. If you have you understood, type in yes or no. Then I'll move to next. Okay, clear. So we can take up the questions, right? We can take up some tricky questions. Okay. All of you, please answer. Aditi, Anusha, Arya. Arya is not speaking today at all. Parvati, Arabi, Sanmukh. Okay. Let's take up the questions we have. We'll take the simple ones first. We'll not suddenly jump to the difficult ones. Draw the free body diagram. Same string, same tension. String pulls everything that it is in contact with. Kshitij is done. Aditya Raj is done. All three masses free body diagram. M, 2M and another M. All three. Oro, Ansh. Okay, let us see how to go about this. Quickly, I'll do it. I am assuming that all of you have got it correct, absolutely correct. For records, let's quickly draw this. mg down, let's call it as N1. This is mass M at the top. At the bottom, there will be 2 mg, normal from the bottom surface, no, the pair of the normal direction from the top. This is 2 mg. This is, let's say, N2. This is pair of N1. This is the tension. You might be probably thinking that pair of N2 is where? Pair of N2 is on this surface down. Okay. So this is T. Now on the mass that is hanging, this is T and that is mg. Fine. So this is the free body diagram. If you want to draw the free body diagram of pulley, you need to just show T here and T there along the string. It will pull the pulley also like that. Clear to all of you? This is how we have to draw. I am assuming all of you have got it correct. Absolutely correct. Those who have done it. All right, good. Let's take up the other one. Oh, here we have friction. Do this. I'll just rename everything. All of you don't use the values. Is theta, M1, M2, and M3. Do it, all of you. I'll just fill up the water and come quickly. Anusha is done. Ansh, Aditya, Kshitij. Arya is done. Aditi is done. Okay, let us draw it quickly. Good. There is M1. On M1, we'll have M1G. And we'll have, let's say, tension T1. Okay. On M2, there's M2. On M2, along the incline, what is the component of Mg? How much this will be? Mg sine. M2G sine of theta. This component will be M2G cos of theta. I'm directly writing the component. I'm not drawing Mg. This is N. There will be a tension over here T2. And one string will pull it down from here T1. Okay. Now M3. This is M3. M3 will get pulled down by M3G, and this tension is T2. How many of you got it correct? Oro, Gurman, Ansh, Aditya, Aditi, Oshik. Okay. Why isn't T1, T2 same? What is the answer to that? Why T1, T2 are not same? They are different strings. They're different strings. The thumb rule is same string, same tension. If string changes, tensions will be different. Okay, great. We'll take one more and then we'll study friction. Everything can move. A, B, and C can move. And masses, again, I'll rename everything. This is theta. This is M3. This is M2. This is M1. Draw the Faber diagram of M1, M2, and M3. Done. Ansh is done. Kshitij, Oro, done. Okay, let's see. Aditya is done. Okay, let's do it now. If you get this right, you have understood everything about tension and normal reaction. First, we'll draw the M3. This is M3G sine theta, M3G cos theta. This one is a normal reaction. Let's call it as N3 because it is M3. And this one is tension T. This is the free body diagram of M3. Okay. Now let us draw the free body diagram of M2. This will be tension T, same string, okay? Entire string is same, a single string is used. This is M2G. Is that it? Am I missing something? Free body diagram of M2. Normal from where? From M1, it will get pushed like this. Okay? Because of this normal reaction, M1 when it moves will also take M2 along with it. So M2 not only moves down with acceleration, it also moves forward with acceleration of M1. But the acceleration part we are not doing today. We are doing only force part. This is M1. So never remove pulley which is fixed to any mass. Pulley is a part of mass. So when you draw the free body diagram of M1, pulley comes along with it like this. Okay. So this is M1. There will be tension T and T. Both the points are getting pulled like that. There will be M1G. There is, let's call it as N2. There is N1. That's it. Is that it? Where is the pair of N2? Who is applying N2? M1 is applying on M2. N2. So M2 will apply on M1. N2. This is the free body diagram of M1. Assuming most of you have got it, maybe some silly errors here and there, that is fine. Is all fine. Any doubts with respect to this question? Anyone has any doubts? No doubts? See this M1, if it is going like this with acceleration A, acceleration of M2 horizontally will also be A because there's a constraint. Along the normal, M1 and M2 should have same acceleration horizontally. So both will have acceleration A. But M2 is also going down with some acceleration, let's say A2. Okay. And this is going up with, let's say, acceleration of A1. All right, guys. So let us move forward to, let me see if I'm missing any question. Otherwise, we'll talk about friction. Okay, this one. And then we'll talk about friction. So there is this lift mass is capital M, and this person's mass is small m. The person is inside the lift. Okay, you need to draw the free body diagram of person separately and only lift separately. Person is pulling the string to hold himself. Done. Aditya is done. Okay, fine. We'll quickly draw the favor diagram. This is a person. It will experience tension T. It will have mg down and it will have a normal reaction N. How many of you got this correct? Any doubt in this? Okay, now the lift part. This one is lift. On the lift, pair of N1, because lift is applying N. So there is a pair of N like that. The lift has gravity force, capital Mg. Okay, and there is a tension force T like this. This is the free body diagram. I'm sure here some of you might have done some silly error. Is this correct for all of you? What about small mg? Small mg is Earth applies on small m. Why Earth will apply small mg on capital M? Won't there be a tension force from here also? That also you might have drawn. M is not a vector quantity. M is a scalar. There is nothing called component of M. Is this will be present or not? This will be present or not? Why? Why not? Why not? Not in contact. The string, this string is pulling only the person. This string is not in contact with the capital M. If it is in contact, then only it will apply the force. Okay, it's not part of man. It is a string. Okay, All right, so let us discuss a little bit about, should the lift be m plus mg? See, this n will take care of it. When you do the force balance, this n will take care of the load because of the person, because of this person. You'll have, it is stationary, so I can say T plus normal reaction upward force minus mg should be equal to 0. So n will be equal to mg minus t. So there is this downward force also over here, which will take care of it. Okay. But small mg doesn't get applied on the capital M. Small mg is the force Earth applies. The force Earth applies is on the mass of small m, which is mg. Why Earth will apply small mg force on capital M? On capital M, capital mg will be applied. Okay, so it is not that things are complicated. You are complicating it yourself to you. So like this, what will happen? You start assuming things and mechanics becomes day in, day out. If you start assuming these kind of things, it will get accumulated and you start feeling mechanics is very complicated. But reality is mechanics is straightforward if you keep it simple. Okay, so let us discuss a little bit about friction. All of you write down. Normal reaction is perpendicular to the surface. It is a reaction from the surface in perpendicular direction. Write down, friction is reaction from the surface in parallel direction, in parallel to the surface direction. Okay, whatever you know about friction, please type in. I mean, whatever little bit of idea, or if you have good amount of idea, whatever you want to say, please type it out. Don't worry, I'll not take anybody's name. Just type it out, whatever you know, so that I can understand what all things I have to clear. Acts in opposite direction of motion. Okay. Opposing force. Friction supports motion. Okay. What else? Keep on writing. Others also please participate. It's not that all of whatever they have written is correct. Okay. Static and kinetic friction comes into play when there is a contact. Is that it? Okay. Smoother the surface, lesser the friction. Very good. What is the cause of the friction? Cause of the friction is what? What causes the friction? Surface roughness. Very good. Surface roughness actually creates some sort of interlocking. What does it mean? Let's say two surfaces are in contact. Let me draw it. There is this surface and onto which a block is kept like this. Okay. Of course, it is in contact, it's not in air. So it is in contact. Now, because the surface is rough, if you zoom in, at a very granular level, you'll see some sort of interlocking like this. I'm just representing it, okay? It's not exactly like this, but this is what it represents. This is the surface of the block, and that is the surface of the floor. They are interlocked because they are not smooth. It may appear that they are smooth, but in reality, they are not. Okay? So when this object tries to move relative to that surface, okay, if this velocity equal to that velocity, then no problem. Nothing will happen. But if this velocity is greater than that velocity or lesser than that velocity, then because of interlocking, the one surface cannot move freely with respect to the other surface. Are you getting? They are interlocked. So if you want to make sure that they are moving together, it will be allowed. But if one surface wants to slide on the other surface, if the upper surface has lesser or more velocity than the lower one, then the interlocking won't allow it. So this is creating the friction. Fine. Now let us see at a macroscopic level what is happening. Suppose this is mass m and you are pushing with, let's say, very small amount of force, let's say 1 Newton force. Achha, by the way, let's say 1 Newton force is not there right as of now. No force is there. No force. I'm not pushing this mass at all. How much is the friction acting on this mass? What do you think? What is the amount of friction acting on it? Zero. It is zero. If you say it is not zero, let's say it has some force of friction acting on it, then the total force on this mass, horizontal direction, is F, which is friction. It should start moving automatically by itself, which doesn't happen. So if you're not applying any force parallel to the surface, friction force will be zero. Okay. Now when you are, let's say, applying 1 Newton, you are applying, let's say, 1 Newton of force and the block doesn't move. Now what is the force of friction? How much it is? You are applying 1 Newton, the mass doesn't move. What is the force of friction applied on it? And in which direction? More than 1 Newton, some of you are saying, and most of you are saying exactly 1 Newton. Okay, let's take that first. Let us assume that more than 1 Newton is applied. Let's say in this direction, 2 Newton force of friction is getting applied. Okay, so total force is how much? 2 minus 1, 1 Newton total force is there on the left hand side. So it should start accelerating on its own in the opposite direction of which force you are applying, because total force is not zero. Fine, but I know that the mass is at rest. If mass is at rest, total force should be zero. Fine, so force of friction has to be equal and opposite, then only total force will become zero. Fine, so friction is 1 Newton only. Now if I increase the force, if I add 1 more Newton, still the mass is not moving. Now how much friction is acting? How much? Now friction will also adjust itself, 1 Newton. So this is something amazing, that friction adjusts its value. Write down, friction adjusts its value till sliding starts. Okay, friction will keep on adjusting its value, and once the mass starts sliding, once sliding starts, force of friction will become constant. So the interlocking will oppose up to a point, and once interlocking is broken and now it is riding one on top of the other, the opposition is more or less same. Getting it? Understood? Now tell me one thing. The maximum value of friction will happen when the interlocking is about to get broken, or it is applied when it has already started sliding. Have you understood the question? Interlocking when it is about to be broken, then friction will be maximum, or when the interlocking is broken and they are sliding now? When it slides. It is when it is about to be broken. Just imagine this scenario. Just imagine it. It will oppose, right? It will oppose the motion. This kind of, I don't have any interlocking to show you, but right now, suppose you have interlock your fingers like that. So right now the opposition is very high. As soon as this interlocking is broken, now you can see the opposition is lesser. Till it is locked, it will oppose the maximum. Once that locking is broken, now they will have lesser friction. So maximum friction will be when it is about to be broken. Okay. So if you draw a graph of force of friction, if you draw a graph of force of friction, let's say let's say y-axis is force of friction and x-axis is the force which you are applying. Okay, so till the object is not sliding, your force, whatever you're applying, and friction, they'll be equal. So you'll get a straight line. When you increase f, small f also increases. So what is this angle? Anyone? This angle will be what? Both should be equal all the time till it starts sliding. Correct. It will be 45 degrees. Then what will happen? It is about to slide now. What will happen now? Friction will dip little bit. It will be lesser. And then it will become constant. Getting it? This will what happen. Till here, we call this zone is called the zone of static friction. This zone is called zone of static friction, where there is no sliding, relative motion is zero, there is static friction, and this one is kinetic friction. Kinetic friction. Okay, fine. Now, one more question is, now I'm trying to define how much is a friction force. As most of you have already said, friction depends on the roughness. Very good. It depends on the roughness. Roughness, area of contact, whatever you want to say. It depends on that. What else force of friction depends upon? What else it depends upon? Okay. Force applied, I'm talking about the kinetic friction here. Yes, force depends upon the force applied. Friction depends on the force applied in case of static friction. Both are equal and opposite, definitely. But in case of kinetic friction, what the force of friction will be proportional to? Take, for example, two surfaces like this. What is kinetic friction? Kinetic friction is the constant friction that gets applied once the two surface starts sliding. It is constant. Friction will be constant. That is a kinetic friction. Nature of material comes under roughness only. Okay. Now look at these two surfaces. They are in contact. Right now, I am not pressing very hard. It is like this only. So they slide very smoothly. Now, if I'm pressing it hard, now do you think friction will increase or not? Friction will increase? Yes or no? So what is this pressing hard? Which force is this? Pressing force is what between the two surfaces? Normal force, not gravity. Gravity is the force Earth applies. Gravity force doesn't change. Gravity remains mg. Gravity remains mg. Fine. It will not change. What you are doing it, you are not increasing gravity when you're pressing it. When you're pressing it, you're increasing the normal force between the two surfaces. Fine. So friction depends upon the normal force. And when I club these two, I'm saying that this is kinetic friction. We are doing it. Kinetic friction is written as Fk. It is equal to mu times normal reaction. Mu k times normal reaction. Mu k is a constant which depends on the property of the surface. Okay. This is kinetic friction. Mu k is the kinetic friction coefficient. Mu k coefficient of kinetic friction. Understood? Now similarly, the static friction is not constant. It will range from 0 to the maximum value. So maximum value of static friction can be written as mu s times normal reaction. So static friction is less than or equal to that, because static friction can be changed between 0 to the maximum value. Kinetic friction is constant. When the object starts sliding, when one object starts sliding on the other object, kinetic friction starts. Before that, static friction can adjust its value. The kink in the graph, static or kinetic? Static, static. The maximum value, the top is the static. What is mu s? Mu s is coefficient of static friction. Coefficient of static friction. Tell me, mu s will be more or mu k will be more? Which one will be more? Which one? This is the maximum value. This is the maximum value of static friction. And this is the kinetic friction. So you can see that maximum value of static friction is slightly more than the kinetic. Fine. So hence, mu s is slightly more than mu k. Mu s is slightly more than mu k. If it is not given in the question, what is mu s and what is mu k, you consider both mu s and mu k to be equal. Any doubts to anyone? Does inclination of surface matter? No. Because of inclination, normal reaction will change. So friction will change because normal reaction has been changed. But coefficient of friction depends on both the surfaces in contact, because interlocking depends on both the surfaces. Coefficient of static friction is a constant. It represents the material, how rough the material is. If μs is more, roughness is more. That's what. Any other doubt? Any other doubt? Acha, can you tell me which direction the force of friction will be? Force of friction direction will be which one? Opposite to what? If two surfaces are moving with the same velocity, friction is zero. There is no relative motion. Which direction? Yeah, it is parallel to surface. Parallel to surface, two directions are there, forward and backwards. So it is opposite to, write down, opposite to relative tending motion. Tending motion, relatively where the object is trying to move. Because friction can be present even though there is no movement. For example, in this case right now, in static case, there is no movement. So we need to check relatively where the object is trying to move. Opposite to that will be the force of friction. Okay. Yes, or oh, that is different. Okay, we are not discussing that. Even normal direction will not be there if you do that. If you are in the air. Okay. Any doubts on friction? Anyone has any doubts? We'll be discussing friction in much greater detail when we do this chapter. Right now, we have just introduced it. No doubts. No doubts to anyone. So we'll take one question. We have time for one question. Okay, we'll do it. Any doubts on whatever we have discussed? Why max of static is greater than max of kinetic? I mean, it is a qualitative explanation. Quantitatively, we have not proved it. I'm saying just you can experience it. If there is an interlocking, till the interlocking is broken, it will attain a maximum amount of force, and as soon as interlocking broken, now you'll feel that lesser force is there. When they're moving on each other, lesser force of opposition is there. But when it is about to be broken, it is like this, the force opposition is higher. So that is why the maximum value of static friction is higher than the kinetic friction. Maximum kinetic friction doesn't mean anything. Kinetic friction is constant. Once the object starts sliding on the other object, kinetic friction becomes fixed. Friction is mu k into n. It is a constant value if object is sliding on the other object. Okay, shall we take one question? Just one question. Okay, we'll take one question and that's all then for today. Friction. Okay, where is friction? This one. Assume that the, let me first rename everything. This is last question for today. Do it diligently. This is M1, M2, M3. Coefficient of friction is mu2 and mu3. So between M2 and the surface, coefficient of friction is mu2. This is M3. And between M3 and the surface, coefficient of friction is mu3. All right. Assume that M1 is going down with acceleration A. So will all the acceleration be equal or not? All of you tell me, all of their accelerations will be equal or not? The reason is constrained motion. Constrained motion, right? So correct. So all of you please draw the free body diagram. For the three masses, draw the free body diagram. Last thing for today. Free body diagram of the masses and the floor also. This is actually the last question of bridge program. Bridge program will be over after today. Okay. So from next class, we'll start the class 11th curriculum. So bridge program is done. Oro is done. Others? Arya is done. Gurman. Okay. Let's do it now. M1. This is M1. On M1, M1G, and there is a tension T. So when we represent acceleration as a vector, acceleration vector should not touch the mass. So if you want to represent acceleration also, you can show it like this. Acceleration is not force. This is, let's say this is T1, okay? Then M2. This force is T1, okay? Then this is M2G. This is N2, let us say. There is, let's say, T2. Acceleration is like that. Friction force, how much it will be and in which direction? How much will be the friction? It will be backwards, right? How much? Correct. Mu2 into N2. It is sliding, so friction will be constant because it is a kinetic friction, right? Had it been at rest, had it been not sliding, then we have no idea what is a friction. Then we need to do force balance and find out the friction. But right now it is sliding. Because of that, friction is constant. Now M3. M3 will have tension in that direction. Sorry. This tension, which is T2. Then this normal reaction, let's call it N3. This one is M3G. And M3 is sliding forward. So there will be a force of friction that way, which will be mu 3 N3. No, you should not write signs here. Okay, directions, when you're representing the directions, automatically it includes it. If you say that force is minus mu2 n2 this direction, it means mu2 n2 is acting on the right hand side. You're showing directions by arrow, not by the signs. Now, the last free body diagram is the surface surface has a pulley like that. So pulley will experience tension like this, tension like that. Pair of N2, this, pair of N3 like that. Is that it? Is that it? Or something I'm missing? Who is applying mu to N2? Who is applying? Surface. The pair of mu to N2 on the surface in opposite direction, right? So I told you at the start, you'll be making silly errors in Newton's third law, not in Newton's second law. Okay, so pair of, just like pair of N3, pair of friction as well, mu 2 N2, and this one, sorry, this is mu 3 N3, this is mu 2 N2. Tell me, any doubts to anyone? All right, guys, so that's it from my side today. We will meet next week. Probably we'll have a quiz before we start the class 11th curriculum. Whatever it is, the bridge program is completed. And all of you, I'm sure, might have learned many things, and it will all help you later on only. You will realize that you have, if you have worked really hard, it will all help you. So I'll send a worksheet. You need to just draw a free body diagram of all the questions. Okay, you don't need to solve it to get the acceleration or anything. Just look at the diagram, draw the free body of that. That's all. Is same friction if sphere and block have the same normal direction and same motion? Yeah, everywhere. Mu 2 and 2 doesn't matter. If there is a, if let us say, if there is a sphere in contact with the edge like that, okay, like this, the normal reaction will be like this, normal direction, and friction can be like that. Friction is parallel, tangential, normal is perpendicular. All right, guys, so that's it. We will meet again next week. Till then, take care and bye-bye.
Thank you, sir.